so we wrapped up last class. Yes, sir. Yeah, I think so. I mean, let me get back to you, but I think it should be fine. Yeah. Again, I'm not quizzing you on the equations, and you're allowed to plot and stuff. Integration to confirm your integration. I think it's okay, but I'll get back to you on that. Good question. I would say yes, but I want to make sure that this is what they've been doing in the course before, because I've never taught this course before, right? So I would push for that. It's allowed. So I think it's reasonable to allow it. So anyway, so let's wrapped up. We wrapped up last time when we were talking about capacitors. So I think where we stopped was we said that you can design a specific capacitance based on selection of the area of the plates, the dimension or area of the plates, the distance between the plates where the charge is deposited, and the dielectric constant between the plates, right? So we said that the dielectric constant of air, which is epsilon naught, is a certain given value that does not change, and then dielectric constant of the material, if you have any other material in there, will be epsilon, which is equal to epsilon naught times epsilon r. So it's the relative dielectric constant multiplied by the dielectric constant of air. That will be the dielectric constant of a material in here that is other than air. So you multiply both by each other. So the next slide is basically a direct application of this equation. It's just a direct application. They give you two plates with a certain area and a certain distance between them, and they have two different dielectrics in there. One time they tell you, okay, consider the dielectric is only air. Other time they can tell you to consider the dielectric is mica and has a relative dielectric constant of a certain value. So just substitute in the equation twice, and obviously in the case of mica, we have a much bigger capacitance. The reason is it has a better electrical insulation properties, right? So if you're using materials with better insulation properties, for the same size capacitor, you can get a bigger capacitance with. So questions on this? So as we said, lots of people are working on these electrically insulating materials, trying to improve them, trying to make them operate for higher temperatures, freezing temperatures. That's where research is in capacitors. Okay, inductance. So we the analogy for inductance in a fluid circuit we said was this water wheel that does not allow water, or in this case in the electrical circuit, current to change abruptly, right? So the water wheel would sort of dampen the change of the flow of water out of it, and the same thing, the inductor dampens the flow of current flowing through it, right? Does not allow current to change abruptly. That's how the inductor sort of functions there. Why do we need to use these inductors in circuits? Because like capacitive elements, they are an energy storage element that does not dissipate real power. They do not dissipate power while storing the energy. Ideally speaking, of course. Practically, these inductors are basically made of wires. They are basically made of electrical wires, and you can wind them around the core or not. Does not really matter. If you don't put a core in the middle, then you don't have a defined place for the flux to flow, right? Then flux can go in many different directions. You would like the flux to flow in a certain defined path so that it can link all the turns of wire that you have, that you're pushing current through. If you're not linking all these turns, then the voltage then you're not storing the flux around this inductor uniformly. You link all of these, you're defining the path, then all the flux lines are gonna be flowing through this core and linking all the turns, right? So any current flowing in any of these turns will create flux that is confined to a certain space, that is adding up to all the flux that's stored around this inductor, right? If you don't put these cores, then you don't have that sort of luxury, and you need to sort of push a lot more current to be able to have the flux, the same flux link the same number of turns, right? So it's just having this material in there, the magnetically a magnetic material, magnetically conducting material is something that is to your advantage. It helps you define the flux line, the flow of flux lines within a certain region, so that it links all the coils in a certain way, so you're storing the flux around the inductor. So these inductors come in many different shapes and forms, and the material that you use in there is sometimes what defines these shapes and forms. So sometimes this material is like a transformer that you see, the power transformers. These materials are basically sheets of steel, like we have in this example, big sheets of steel, right? Sometimes this material is a powder that's compressed, like these are called toroids. So you see some of these toroids. This is a compressed powder. It's magnetic material that is created in powder form and compressed in a certain shape, right? So they can come in many different shapes and forms, and of course, the losses. If you have a magnetically conducting material, then anytime you have a time varying flux in a magnetic material or any magnetic material that sees a time varying flux, will see current flow through it, right? If you have a piece of wire and a time varying magnetic field, then current will flow in that piece of wire. If you close the loop, then if you have a loop there and close it, current will flow, right? So this current will do the same in the magnetic material. These sheets of steel, current will flow in the sheet of steel. Sheet of steel for a magnetic is basically an electrically conducting material and a magnetically conducting material. Steel is electric conducting and magnetically conducting. In this case, you have a magnetic material that is seeing a time varying flux. It is also electrically conducting, so you will have current flow in it because it's nothing but a sheet of steel. It's like a closed loop, right? So you will have small loops of current flowing in this material, causing losses, right? So these losses depend on the frequency of the applied magnetic field, and that's why you have these different shapes, because these different types of materials behave differently for different frequencies of the applied magnetic field, right? That's really the reason why. So at the end of the day, you just want the inductance, really, but you want a certain inductance, 1 millihenry, for example. It's not the same as if you take this inductance and plug it into a circuit operating at 50 hertz. It's not the same as taking this inductance and plugging it into a circuit that's operating at 100 hertz, right? The frequency affects the losses in the material, right? So that's why we have these different materials that are used. So the same thing we did with the capacitance. We want to find the relationship between the voltage across the device and the current flowing through the device, and of course the energy stored in the device. Right? That's really what we did with the capacitor before, and we will do the same thing with the inductor. So the voltage at the terminals of an inductor is defined by this equation. The voltage at the terminals of the inductor is equal to the inductance multiplied by the time varying current flowing through it. Okay, and this is again from Faraday's law, right? So basically we have current flowing in a piece of wire. These wires are stacked into turns. These turns create flux using the right-hand rule. These flux lines link all these turns and hence produce a voltage across the inductor. Right? So this voltage in this case is equal to L di by dt. Right? So it depends on the current that created it. So if the current is not time varying, if you have a DC current in there, then the voltage across the inductor is 0. The unit of inductance is H or Henry. So, I'm sorry, this is cut off here. But the unit of inductance is Henry. And the inductor stores energy in the form of flux created around the inductor. So you create this flux, it's storing energy. Then you can basically as soon as you charge this inductor, you can automatically take it, plug it into another circuit, and this flux will collapse because you're not supplying it like the capacitor. With the capacitor, you were putting in, it's like the channel analogy where you're putting in water into this channel to raise the to raise the pressure. You have to raise the pressure of the diaphragm at the bottom. Here it's very similar. So instead of in the capacitor, you were raising the voltage by applying charge. In an inductor, you apply voltage, and what you do when you apply voltage is you build flux around the inductor. Right? At some point, the capacitor was doing what? At some point, you cannot put more water because the diaphragm will rupture. It has a certain pressure rating. Same thing with the inductor. The inductor, you keep trying to push current to increase the flux stored around the inductor. The material that you have this flux confined to has a flux carrying capability, will saturate. Right? So after some point, you've pushed the maximum amount of flux that you can push through a certain material. After that, you're doing what? You're just pushing current for no reason, because you're not getting additional flux, because your core has already saturated. The path that you've defined for the flux to flow has filled up. So you can raise the voltage. What happens if I raise the voltage in that case? I put a power supply and I raise the voltage. Current will increase. Of course, current will increase because it's seeing some impedance that's certain value. But this impedance, this current increase is not going to correspond to an increase in the flux that you have. Right? So you will see an increase in current, but it will not be increasing flux. So if you're not increasing flux, what are you doing? You're not really making an inductor anymore, you're just burning power. Right? So same as the capacitor, it has a limit. The limit is the flux density of the material that you're winding this core around. Okay, so if the voltage is related to the current by this differentiation, then for me to calculate the current through the inductor, I would integrate the voltage, right? I would have to integrate the voltage and add to that any initial conditions, right? The initial condition is where the point that you've charged the inductance to, right? You've charged it to a certain value. This amount of energy that's in there is going to be dependent on current. And this current will, if you take this inductance and connect it to another circuit, it will flow through that other circuit and dissipate the amount of energy that's stored. Okay, so power is the same as any electrical circuit. Power is defined by voltage multiplied by current. Going back to the relationship between voltage and current through an inductor, forget about this Q, it's a typo. The voltage and current is defined by this equation. So if I substitute V in this equation for power up here, I get the instantaneous power through an inductor is equal to L I of t times D times I of t. If I is changing, then I bring this inside differentiation. So it's I bring dt on one side, so I bring dt on one side. If I bring dt and multiplying it by power, and I integrate both sides, so p of t dt, and then L times I of t di of t. I integrate both sides with respect to time. What do I get? Energy on one side. The integration of power with respect to time is energy. And then the integration of L I of t di of t will be Li squared. Half Li squared. Right? So the energy stored in an inductor is equal to half Li squared. What was the energy stored in the capacitor equal to? Half CV squared. Right? So one depends on the voltage, one depends on the current. Right? So they're always analogous. So this is a summary of what we just said, that we have a relationship that governs the voltage and current across an inductor, and then we can calculate the inductance, the current to the inductor, and hence the energy to the inductor. So the next thing we'll do is a similar example to what we did with the capacitor. So in this case we're given a 5 Henry inductance, and also Henry is a big quantity. Okay, so these inductances that you will typically see on an electronic board will be millihenry, microhenry sort of ranges. If you're talking about an inductance that you will see in a big drive, in a big piece of equipment that is used to run the LNG compressor for the RAS gases train 1 and 2, for example, maybe 1 Henry. And it's huge. It's a big chunk of the big cabinet that you see. One third of the cabinet almost. These big drives that are used to run these big motors that run the compressors. One third of the cabinet may be an inductor, and then maybe another third of the cabinet may be some capacitors and the control unit, and then the power device. These things are huge in the power system. So typically you don't see a 5 Henry inductor. You will never see that. You typically see things in the millihenry, and there's no in the capacitors. We said that there are companies now developing what is called supercapacitors and ultracapacitors, and these devices are small. These are small devices that you can actually store a decent amount of energy in them. And inductors, to store a reasonable amount of energy, you have a much bigger frame, right? So typically people don't use inductors for energy storage as such. They sort of use it more to filter out ripple, right? So like the water wheel, right? The fluid analogy is very nice, right? You have a channel where you can store water in. You would store water in a channel, but the water wheel is not something where you would store the water, right? It's just something that you would sort of use it to filter the water flow, right? So it's very analogous to the water flow example. So anyway, so back to here. So we just apply basically the equation that we were just talking about, right? You're given, I think you're given the current, and they ask you to plot the voltage and the power and the energy stored, right? So if you're given the current I of t, we go back to our equation which defines the voltage and current relationship, right? So voltage is equal to L di by dt. So I differentiate this equation, this waveform, and I will get the voltage. So anytime there's no change, right? There's no change when it's zero. You expect the current to be zero. And then here, it's the slope of this line. The differentiation is basically the slope of the line. So this is delta y is 3 and delta x is 2, right? So and the index, so it's 1.5, right? So 3 over 2 is 1.5, and then L is 5 Henry, so it's 5 times 1.5, which is equal to 7.5 volts. So 7.5 volts, and then it's 0 because the current is not changing. 0 because the current is not changing, and then here it's delta y is 3, delta x is 1, so it's the slope is negative, right? So I multiply 5 by minus 3, which is minus 15. So this is my voltage waveform across the inductance, right? Energy storage is half Li squared, right? So it's half times Li squared. I is given here. So sorry, they do power first. Power is just the V times the I, the voltage times the current. So they take this, multiply by that. So you get a ramp here, you get a 0 in this zone, and then you get another ramp in this area, right? I won't do these calculations. And then energy is the integration of power. So you have a ramp, you integrate it, you get a squared, a quadratic, right? So ramp, you integrate, you get a quadratic. A ramp, you integrate, you get a quadratic as well, right? But it's all positive because the current is squared, right? So any questions on this? Right, so here we integrated this and we got this quadratic, and then remember so we stopped at this point, right? So this is energy. Energy does not go down to zero, right? So energy so far is a certain value. Energy does not increase. There's no additional energy being stored in this inductance, so it just stays constant and then goes back to zero. So any questions on this? It's just an application of the equation here. And like we did with capacitors, sometimes we need to develop circuits with different variations of inductance in the circuit. Why? Sometimes you want to put an inductance in the circuit, but maybe the voltage rating, right, is too high. Right? The voltage that will be developed across that inductor is too high. Remember, D will be L di by dt. So there will be a voltage developed across that inductor. This voltage will be the sum of the voltage across each of these individual turns in the inductor. Right? So there is a voltage difference between the actual turns in the inductor. So you have to insulate the wires of the inductor. It's not bare copper. Right? It's insulated turns. Right? So if you have a very high voltage and you want to put an insulation around this material, you need space. Right? So sometimes you just cannot, build one big inductor, for example. You maybe have to divide it up into different smaller size inductors. Right? So you end up requiring, or you want to increase the current rating of an inductance. For example, if you want to increase the current rating, you need to use a very big wire. If you cannot use a big wire, what do? Maybe put inductors in parallel, right? So inductors in series they behave like resistors. So you add them up. When they're in series, you add them up. Capacitors, when they're in series, the equivalent is the reciprocal, the sum of the reciprocals. Inductors, when they're in series, you treat them like resistors. Right? You just add them up. And then when they're in parallel, they're also like resistors. You add the reciprocal. So this is the proof. And the proof is very similar to what we did last time with the capacitors, right? So they looked at using Kirchhoff voltage law, the voltage at the terminals is the sum of the three different voltages developed across the three inductors. And then they wrote down, okay, the voltage across one of these inductors is equal to L di by dt. So you have three of those added. So this is the total voltage is equal to the summation of inductor plus multiplied by di dt. Which di by dt is the same, so it's a common factor outside. So basically, the sum of the inductances, or the equivalent inductor, is the sum of the three inductors in series. Okay, so that's equivalent inductance in series. In parallel, again, to find the equivalent inductance, you add the reciprocals of the inductance. So the equivalent inductance is 1 over the equivalent inductance is equal to 1 over each of these inductances separately, and you add. The proof is similar. I'm sorry, when I converted to PDF, the summation terms under the sum for some reason became big there. So, but the proof is very similar. So the total current is equal to the sum of the individual currents. The individual current, if you forget about the initial condition, is equal to 1 over the inductance, 1 over the individual inductance, multiplied by the integration of the voltage. The voltage, since they're all in parallel, is the same. So the integration of the voltage is the same. So that can stay outside, and then you have to sum up the 1 over each individual edge. And that's why the equivalent inductance is 1 over the individual inductance. 1 over the equivalent inductance is equal to 1 over each of these inductors summed together. Okay, so that's inductors, series, and parallel. Then simplifying circuits with inductors is similar to what we've done before for resistors and capacitors. So if you have, in this case, for example, you have a circuit that looks like this, how would you work with this? These two are in series. This 2 Henry is in series with 3 Henry. You just add them up, right? So this is 5 Henry. 5 Henry parallel with 5 Henry is what? Which is 2.5. Right? Anytime you have two resistors that are in parallel, the equivalent is half of it. So that's 2.5 Henry. So 2.5 Henry in series with 1, so you end up with 3.5 Henry. Okay? And this is very similar, right? So you have 2 Henry in series with 3 Henry, that's 5. 5 in parallel with 4, in parallel with 5, right? So the equivalent is 1 over the equivalent is equal to 1 over 5 plus 1 over 4 plus 1 over 5. Then you find the equivalent of this group here. And this group here is in series with this, so you just add, and then add this as well, because they're in series together. Okay? The math is here for you to... So this really wraps up chapter 3, which is where we will stop on the exam, or this first exam. So any questions on any of the previous materials? So the homeworks are there, make sure you solve them. You have a quiz in the next lab. I think you should be prepared. And we're done early with the material, so you should be able to hopefully have enough time to study. So if you don't have any questions, I'll move on to start chapter 4. It will not be included in the exam, but we'll get started. Okay, transient analysis. So we talked a lot about, having, yes ma'am. Oh, you want to stall me so you don't get into material? I'm just kidding. No, I'm just kidding. Yes. The book? No. No. Does anybody have a book? Well, what's the question? Yeah? You have a picture of it. Honestly, it should be very close to the homework. I mean, circuits really is solving homework. The practicing solving problems. So it's some of the theory we talked about that. I don't think I'm not going to tell you what's the analogy, or maybe it's a good question to give you a fluid circuit and tell you what the analogy is into electrical current. Maybe I don't know. That's not. I think the equation sheet is there, right? I gave you an equation sheet on the website. It should be there is an equation sheet on the website, and I asked you to work with Randa to see if there are missing equations that you've used in your homework that you want to be added there, that want to be added. So I threw the burden on you. So, so if you have things to add, yes.
This question.
Please find the values of I1 and I2 in figure blah blah blah. So let's okay. Let's see. Maybe hard for me too, but because I haven't solved in a while. Right? Find the values of I1, which is here, and I2. This is R1, let's say R2, and then R3, and then R4. So this resistor and this resistor, so R3 and R4, they're connected at 2 points. So they're in parallel. Right or wrong? These resistors are in parallel. R3 and R4 are in parallel. And R1 and R2 are in parallel. So the equivalent circuit to this is what? And this is R equivalent 1, R equivalent 2. For you to find I1, it's just this voltage divided by the sum. Right? So that's I1. Right? I2. I2 is current flowing between these two nodes. Is there a voltage difference between these nodes? Because what? There is? In the solution? Sure. Current to current flow. So let's say, so they said they did Kirchhoff current law here. So they have here, let's say current coming out here, and current doesn't matter. So let's so this is IR1, and then here out, IR3, and this is IR2. And what do we have? So this is my reference node, and so this is, let's say, call this V1. Yeah, so what do we have? So current coming in is equal to current coming out, so IR1 is equal to IR3 plus I2, right? So IR1 is equal to what? Your supply voltage, so this is V supply, so it's V1. IR1 is equal to what? V supply minus V1, V supply minus V1 over R1. That's equal to IR3, which is equal to V1 minus 0 over R3 plus I2. So I have V supply minus V1 over R1 equal to V1 over R3 plus I2. And then they did KCL here as well. You know voltage here, right? You, you know voltage at V1. Yes, you do, because voltage at V1 is the same voltage, right? So what, if you want to do the numbers, you can do it, right? So Vs was 20 volts. So Vs was 20 volts, and then V1 was 10 volts, and then you have R1 is a certain value equal to what? 6 equal to V1 is 10 divided by R3 is 12 ohms plus I2. So that's how they found I2. So what is this? 20 minus, that's 10 over 6, 10 over 12 plus I2. Is this what they got? Okay. But why? Okay. What we said, the only way to solve and figure out is to do Kirchhoff current law, right? So you have to, if you do Kirchhoff current law, you will do Kirchhoff current law here. The parallel, you're confused about the parallel versus series thing, right? Sure. But again, these two are connected at 2 points. Since they're connected at 2 points, they're in parallel, right? Huh? No, I agree. It's confusing. It confused me as well. So. Yes. Yeah, they would not be in parallel. Yeah, there's a resistor here. They would no longer be in parallel. So this would be more complicated to solve. How would you solve this? Yeah, you have to do Kirchhoff current law, Kirchhoff voltage law. Kirchhoff current law here. You call this V2 in this case, not V1, because it was before it was V1. So you call this V2 in this case. Also do Kirchhoff current law here, and you have two nodes, two equations, and two unknowns. You have two unknowns, which is the current, the voltages here. And V1 is 10. I would assume from the voltage, from the Kirchhoff voltage law, from the voltage divider rule here, right? I didn't do the math, but I'm assuming from voltage divider rule Is R equivalent equal to are these resistors all equal? Okay, so if they're all equal, then R equivalent 1 is equal to R equivalent 2. The voltage divider rule says that you will divide the voltage equally among them. So that's why if this is 20, this will be 10. Okay? The resistor, if I have a resistor here, no, they're not in series anymore. Now you have a messed up circuit. I don't know what you have. This is sometimes we do actually. So sometimes we have. I think there is a section that we didn't cover in the textbook, which is why this may be confusing for you. There is a way to sometimes take a circuit that looks like this. Right, this is what we have, like something like that, and convert it to something that looks like this. There is a mathematical tool that allows us to do that. Okay? We did not cover that. I mean, again, there's no need for you to cover that, right? And if we do that, then we end up with what? We end up with then something that looks like this. This is easy for you to solve, right? Because this is a resistor. This and this are in series, right? These two are in series. These two are in series. These two are in parallel with these two, in series with this one, right? So there's a section in the textbook that I skipped. It's about star delta transforming circuits from between star configuration. This is what it's called, the star configuration, and delta type configuration. There's a way to do that, and the way is based on the fact that, okay, let me put this in a box, put this in a box, put this in a box. Right? I put this in a box and I put this in a box. I look at all the voltage here and the voltage here and the voltage here, all the voltages with respect to each other, and I make sure that they are the same. I look at the currents here, and currents here, and I make sure that this current and this current and this current are the same. So all these three currents are the same, the three voltages are the same. If I do that, then what's inside is equivalent, right? So that's where the derivation comes from. The derivation comes, okay, what's inside is equivalent. What's inside will look, let's say it looked like this star connection. You want to convert it to this triangle or delta connection. You will go through the math and you will find the value for each of these resistors to make it consume the same amount of power that this box would have consumed. That's the proof. I think it's in the text, but we skip that section. Okay? So I would be mean if I bring something that I did not cover. And yeah, that section that was skipped. That's intentional. So we skip a lot of stuff that is in a lot of stuff that's in subsections that are in chapters. We skip it just because this is not 214. Okay. So any other questions? Good point. Then. So we have a few minutes left. So let me start with this, and we can wrap up next time. So we continue next time. So with transient response, the idea is to analyze what happens to, we said that the trains will come in with these large capacitors and stop at the charging station, right? How long does the train need to stop at the charging station, right? It will depend on, how fast this capacitor charges, basically. So this capacitor, the speed at which the capacitor charges, is defined by basically its capacitance. So this capacitance is able to allow a certain amount of charge deposited on its plates until it reaches a certain voltage value. Right? So how long does this process take? So this is what we'll be studying in this chapter. So the time domain sort of effect on these circuits that we've looked at. So before we were just looking at the circuits in steady state, and now we will look at it at both steady state and the transient solution. So we will look at a case where we have this train coming in with this capacitance on it, and as soon as it arrives, it connects to the grid. So this connection to the grid is this switch. They turn it on. So what's going to happen? Current will start flowing, right? The current will flow, governed by what relationship? Remember we studied capacitors and inductors, and we said that we have relationships between the voltages across these devices and the currents through them. So we have a capacitor. This is the voltage across the capacitor, VC. Current through a capacitor is IC. IC is equal to C dVc by dt. This is the relationship that governs the capacitor. Right? So it will take time. As soon as I put a voltage across the capacitor, right? If there is time varying voltage across the capacitor, it means that there is current flowing. If I want to look at the voltage across the capacitor, I have to 1 over C integration of IC dt. I have to look at this current and integrate this current with time. So what will be the result? The result is the voltage across the capacitor cannot change instantaneously. If you try to change the voltage across the capacitor instantaneously, what does that imply? It implies that I have a huge dV, step dV, right? This is step dV in no time. That means I have infinite current, right? There's no such thing as that. You do not want that to happen. And if you have a source that can supply infinite current, then this will happen. Sure, this can happen if you have a source that can supply infinite current. But of course, this is not practical, right? So typically, capacitor voltage rises because our sources are current limited. So what will happen is you will see that capacitor voltage will rise with time. Okay? How much time does it take for the capacitor voltage to reach 60% of its value? How much time does it take to reach 190% of its value, right? This is how much time the train will have to stop at the station, right? So also luckily or unluckily, we have all electrical components, wires, etc. have resistance. Even a capacitor, for you to charge a capacitor, there has to be wires for you to deposit this charge on the capacitor. So this has a resistance as well. So we end up with a equivalent circuit that looks like a small R and a C. Right? So these will affect the speed of charging or the dynamics of the charging process. So that's what we study in this chapter. So again, this is just a review of the various relationships that we discussed: the voltage across a resistor, voltage and current through a capacitor, voltage and current across an inductor. Right? So these relationships we look at. These are time domain relationships. Right? They have a time domain relationship here between the current and voltage across the capacitor and inductor. In resistance, there is no time dependence. Right? You put a voltage, you get a current. You put a current, you get a voltage. Instantaneously, it looks the same shape. Both inductors and capacitors are what cause some transient response. So we'll look at how to deal with that next class.